Welcome back to System Software. Today we'll finish up parsing from last time, and then we'll move on to our intermediate language that we're going to use for our compiler, that we're going to generate code from our compiler. So last time we went over the internals of the compiler. We went over a little philosophy about symbols versus their meaning. And where we left off was in talking about grammars and parse trees. So let me first ask about start this with talking about the homework. So I know I didn't cover completely formal grammars and how to write them. Sort of hoping you would do this just sort of by example. Who has an attempt they'd like to share that they did not Google? Did some people's hands go down? Okay, I think you were first. No, white shirt, behind you.
I attempted it.
Okay, so let's take a look at the attempt. All right, take it away.
I did like E, and then like arrow.
E arrow.
N and E.
N and E.
And then type character
Or.
N E.
N E.
And then next line would be the N, and then 0, 1, 2, 3, 4.
Okay, so that's all the numbers, all the digits.
And then I did E.
Okay.
I think I did N, but I also added the operators.
Okay. That seems pretty close, right? Any other takers? Yeah.
I was a little confused on exactly what to do, but I kind of just showed kind of the process of going from postfix to infix, kind of, if that makes sense.
Yeah, it is similar to that. So if the infix version is this, or maybe this was our infix version that we showed in class. This is like a schema that tells you that expressions, you have an expression on the left side, you have an operator, and then an expression on the right side. So what's the postfix version of that? E-E-op. Yeah, that's really all it is, actually. That's go ahead. Yeah, go ahead.
So for terminal, I have two operators, which are just plus, minus, times, division, and parentheses. For nums, 0 to 9.
Uh-huh.
My non-terminals are an expression which consists of the num operator num and a reverse expression which consists of num operator.
So the issue with this is that you also support infix here.
I don't really know.
Okay.
I was kind of confused.
So this is the answer. You just say, just like infix is saying the operator is in between the two expressions, and the expressions can either be another expression or a number. So postfix is just, you have two expressions followed by an operator. And I think most people had done infix and postfix. Yeah.
I actually create my own expression. All these terminals E equals. Okay, so for homework 13, I actually create my own little expression. I said E equals 5, 4 plus 2, 6 minus asterisk. I know.
Okay, let's go over how this works. So this is infix, right? This is what you know as infix. And you can have nested expressions in this notation. So I can put parentheses to make clear where the nesting happens. So this is one E, this is another E. Right? And within that left-hand expression, there is a nested expression. Does this make sense? Is this clear? And then this symbol is the operator. Has anyone ever programmed in Lisp before? Lisp? Wow, okay. Oh, one person, okay. So this probably looks a little bit like Lisp, kind of. This is actually a representation of a tree. This syntax here. You can think of nesting The exact same way that I nested parentheses is kind of a representation of a graph. So this 8 here, oh, let me get the expression back. So this 8 here is its own expression. If we like skip the end part, each of these are their own expressions. And to reflect the fact that 8 and 3 are the two operands for this plus, we can use a tree to group them together. And so this parenthetical grouping is the same thing as this tree grouping. Does that make sense? Question? Yeah.
So I drew like a tree like that. This is homework. Is that how are we supposed to do that?
Well, the tree. So a tree is one expression in the language, but you can think of the grammar as a schema that tells you what all trees look like. So this is one tree for 8 plus 3 plus 2, but the grammar captures what the structure is for any expression. So if I have another expression like 9 times 3, it's going to have a different tree. But all those trees are captured by this grammar.
So like E is an operator, or like the E is an operand.
Yeah, because E can either be an operation or it can be a number. And because E can be nested inside of itself, or another E can be nested inside of an E, you can capture that relationship for a particular string using this tree to capture it.
Confusing though, like
To have the self-referential stuff?
yeah, the same because
It is confusing.
operator is an operand.
So think of it like recursion in programming. So it's kind of confusing to define factorial in terms of itself, right? But one way to think of it is that every time factorial is called, it's called with a different parameter. And so you can think of that as a different function. So instead of thinking of factorial as having one definition, you can think of factorial as having lots of versions of the function, like factorial 10, factorial 9, etc. And so that recursive function is kind of like a template for generating new functions that have out of the parameters. And so this grammar works kind of the same way, where this is like a template for telling you how you can instantiate one instance of E. So one instance of E is 8 plus 3. Another instance of E is just 8. Another instance of E is 8 plus 3 plus 2. And this recursive relationship tells you how you can arbitrarily nest and create an infinite set of these possible strings. I don't know, does that help at all, sort of? If you think of it like recursion in programming, it's really the same idea. Okay. And so for the sum of whatever this expression is, which represents 8 plus 3, can be represented with another expression for that entire expression plus 2. Okay, so don't worry too much about actually being able to write grammars. If you really are interested, you can take my graduate compilers class. We'll learn about grammars and how to actually automatically parse. What's that?
What time is that offered?
You can check the schedule. I think it's Monday, Wednesday next semester. But let me. So what I want to finish up in parsing is how you can, once you have this tree, how you can interpret or compile this language, either interpret it to get the value or compile it to another language like assembly. All right, so if you look at this, let me clear out the rest of this stuff. So to provide some more concrete definitions of this grammar, as I mentioned last time, the terminals are the words of the language. Those are the symbols that are actually expressed. Those are what's spoken. Those are what's in the source file. That's what you see or hear in the language. So what are the terminals in this expression language?
Numbers and operators.
Yeah, the 0, the 1, the 2, the 3, the 4, the plus, the minus, the times, and the slash. You can think of the word numbers. So whenever somebody tells you a number, they say like, well, I'm 10 years old. They don't say I'm about to tell you a number now, 10 years old, right? You just know that that symbol 10 represents a number because of its actual shape, the phonemes that it's comprised of, and also of how it's used in a sentence. So 10 years old, you know from the grammar, the context of the grammar, that it's a number. And so nobody says, hey, I'm telling you a number. That's what non-terminals do. Non-terminals are like an explicit representation, another symbol that you never really have to say when you speak, but they're an explicit symbol that we can use to record the type of this word or the construct that this word is used in. So it's a little bit of a trick question to say, what are the terminals? And if you say the terminals are numbers, well, you're using a meta word for what those numbers are. The numbers are actually 0, 1, 2, 3, 4, or the ASCII symbols for 0 through 9. Those are the actual concrete symbols. And N here, or num, is a meta word, is meta language to say, here is the set of terminals in my language. And by the same token, we can use these meta words, these non-terminals, to describe other syntactic constructs, like a sentence or a verb phrase. Here we're using it to describe a nested mathematical operation, a nested arithmetic operation. Does that kind of make sense? So this, if you look at this tree here, at the bottom, this is what you actually see or hear. This is what the machine sees in your source code. All of this is unspoken. But what a formal grammar does is it makes this unspoken stuff spoken. It makes it explicit. Because the theory is that there is this kind of hidden grammar here. There is this hidden structure to this language that isn't uttered, that's not said in the source code, or it's not said when we talk. But philosophically, we assume it's there. And we can describe it explicitly in the same way we explicitly say utterances in the language. We can describe it explicitly with a formal grammar. Does that kind of make sense, like philosophically? It's a meta language. It's a language describing language. Questions on that? Questions on that part? So in the formal grammar, the non-terminals are symbols, explicit symbols to describe the syntactic construct, to describe these unspoken things in the language, these unspoken structures. And then productions, these are the rules that tell you how the non-terminals form the structure of the language. They tell you what these non-terminals mean, or at least how they're structured. So this rule here tells you that an E symbol, an expression non-terminal symbol, can be instantiated by taking any other two expressions and putting an operator non-terminal in between. So without this knowledge of this grammar, there's no real way to concrete, or there's, without any concept of this grammar, it's difficult to say precisely what this expressions mean. You might be able to do it statistically by looking at past instances of this expression, and you might get that right, but that sort of begs the question of how did the people who got this right answer get it in the first place? But the kind of philosophy here is that without this formal grammar somewhere, there's no sensible way, no principled way to interpret the meaning of this expression. So these rules tell you what all the possible expressions in this language look like. All you have to do is follow these rules and say, all right, well, if I have an expression and I want to make a valid expression in the language, then I follow this rule. I say, all right, I can either pick this E or this E. If I pick this E here, I then have to, I can then expand it into an N. And in order to continue discovering some expression in this language, I can look at the N non-terminal and pick one of its expansions, one of its rules for telling you how you expand this non-terminal into terminals. And you do that over and over and over until you get all terminals in your language. So for instance here, we have an E. We can pick some other E here. We can pick another E here for the left side and eventually expand that into a terminal 8. And do the same thing for this entire tree, and we'll get one of the instances of this grammar, one of the elements of this language starting from our starting symbol. Yeah.
So grammar is the entire expression.
Yeah, exactly. It's a finite description of all the infinite possible, the infinite set of all possible expressions. So that's kind of the cool trick of it, is that this technically defines an infinite set of possible expressions, and it comprehensively describes all possible expressions, at least in this language. But we can describe it finitely using non-terminals, using a grammar to define it. All right, questions on this, at least kind of philosophically, the distinction between a tree for a particular string in the language and the grammar that describes all the strings in the language? So it's a lot like regular expressions. If you learned, I think not everyone learned regular expressions yet, but it's related to regular expressions. Regular expressions do something similar, where they define an potentially infinite set of strings with a finite representation. Okay, so let's see how we can use this. So this allows us to find the kind of hidden structure of our language. And once we know the syntactic constructs that are being used to express this expression, we can use this tree in order to define an interpretation, define the meaning of this language. So I showed this briefly last time, but let's intuitively interpret the meaning of this tree. So we're going to assume that this is an arithmetic expression, and we're going to use the kind of conventional meaning of arithmetic expressions to try to deduce what the resulting value of this expression is. All right, so what's the value of the ASCII 8 symbol in our kind of computer language? Well, that's the number for 8. But in our programming language, we want, and if we want to compile it or interpret it, we want this 8 to be the actual mathematical number 8. So that could be the machine representation 8. That could be some abstract mathematical object 8. But the value of this 8 symbol, the value of this 8 symbol is the math number 8. And so I'll denote this in red to make it clear the distinction between math number 8 and ASCII symbol 8. And let's do this for all of our symbols. Okay, and assuming this plus has the mathematical meaning of addition, how can we derive the value of this expression E? Yeah, so the meaning of this is take the left-hand side, whatever that is, take the right-hand side, whatever that is, and perform mathematical addition to get its value. So what's the value of this E here? It's just 8. So we can make a rule that says whenever we have an expression that expands to a number, we just copy its value to get the value of this node. And same thing for this expression E. And same for this expression E. So now that we know the value of the left and right child, we can interpret the meaning of this plus symbol, this ASCII plus symbol, as mathematical addition. And so what value does that give for this expression? 11. So we apply the mathematical operation of addition to the left and right child. And so now we have the same kind of expression here. So this expression, this rule says you have an E followed by an operator followed by an E. We have the same kind of node here. We have a node, an E expression that has an E followed by an operator followed by an E. So how do we compute the value of this in our rule set that we're kind of making up here?
You just walk the tree, right? Use add.
Well, here we have, so what was the rule we used for E here?
Add.
The rule was whatever the value of the left-hand side is and the right-hand side, use the mathematical addition operation to find it. So let's apply that rule here. What's the left-hand side value? 11. So we already computed it. We don't have to walk the tree. We just have its value by inspecting the child. And we have the value of the right-hand tree as well. So we can just use the exact same rule and apply addition to the left and right child to interpret the meaning of this expression E. Yeah.
You said it's post order, right?
So it's effectively post order because you only evaluate the root once you've evaluated the left and right child. So in this case, you can use a post order traversal to do this. That's not necessarily true for all language interpretation, but for arithmetic expression interpretation, you can think of it as a post order traversal because you need the children in order to get the value of the parent. But it's going to be you can do this in some tree traversal. All right, with me on the interpretation of this tree? Questions about how we interpret this tree? Who's seen this before? Interpreting the arithmetic expression tree. Okay, so not many. Okay, so as long as you get the basic idea that there's really only two rules you need for this. If you have E that just points to an ASCII symbol, well, just get the mathematical value of that ASCII symbol, the integer value of that ASCII symbol. If you have an E that has E followed by op followed by E, well, just take the value of the two children, the E's children, and perform the addition, the mathematical addition operation whenever you see that ASCII addition operator. Yeah?
Are there considerations for cases where the input given doesn't match the expected rules? So if we have a number, for example?
So in C, you've probably seen compiler error, right? Or syntax error. You forgot a semicolon. So in the programming language world, if we can't prove that program can be analyzed with the grammar, we say it's not a valid C program. And the compiler does not even bother trying to compile it. It just says, you did not give me a valid program. And I know that because it does not match the syntax of the language. That make sense? Okay, so we can formalize these rules, or we can write these rules down using what you might call semantic actions, or little snippets of computation that define how you compute the value of this construct or this node in the tree whenever you match this syntax. So let's start with just the numbers. So for my interpreter, in this version of it, whenever I matched the n non-terminal, and it matches based on the ASCII symbol, 0, 1, 2, 3 for n, I stored its value to be just the ASCII value 0. Not a very interesting one. I did a little differently when I did the tree, but you can think of the value of just being the ASCII symbol value. And the rule for whenever you see an expression that just consists of a number by itself, so like this case, the rule is convert that ASCII value into a machine integer. So assuming I have some function, ASCII to int, we talked about it last time. With me so far on these rules? So pretty straightforward, right? It's just rules that tell you that whenever you match this construct in your tree, here is the computation you do in order to figure out the value of that node. And so I just have a little syntax here to say, here's the value, here's how you assign the value. You just take the non-terminal name dot value, and here's how I assign the value. Here's the rule for assigning a value to that node. And then go ahead.
Are all, because you're talking about like meta languages right now, are all meta language as like recursive and have as many like overloading definitions as this example?
You don't have to. There are regular languages, like regular expression languages. And this is like formal language theory. So in regular expressions, they're not nested. Nesting's not possible. So you wouldn't have, you could have a language that doesn't have this nesting behavior. Yeah.
Would you have rules that define or modify other rules? Because for this example, from what I understand, we only use numbers from 0 to 9. Do you make special rules for 10, 11, so almost an infinite amount of numbers? Or
I would just expand the syntax of the language.
But you wouldn't use that with making a special rule?
No, I would just make a new grammar rule that says, hey, here's how you define multiple digit numbers. So, I mean, you could use what would be called parsing context to turn this into a context driven or context sensitive grammar. But there are already, programming languages already have support for multi-digit numbers, and then you can just define that syntactically as well. You can do that with regular expressions as well. Yeah.
Does this keep going for 2-digit numbers, or does it like put these two single ones together?
So no, this is single digit numbers. If you wanted to do multi-digit numbers, as Martine was asking, you can define a grammar that allows for multiple digit numbers. All right, other questions on this part here? So we just get the value by converting the ASCII symbol to an integer. And so this kind of defines the meaning of this grammar construct. This defines the meaning in terms of how you compute the value of the result. So then for our other operators, we can compute the value exactly as we said in our rule. We take whatever the value of the left child is, whatever the value of the right child is, and we use numbers to kind of disambiguate which E we're talking about. And then we just perform, assuming we have a function in our interpreter called add, we just perform the mathematical addition in order to compute the value of this expression once we match it in our input. Questions on that? Does that kind of make sense? This probably seems a little trivial, right? Like almost tautological, that why do you need to do this? For arithmetic expressions, yeah, because our programming languages already support arithmetic expressions, so we're kind of just translating representations. But the key idea here is that you can formally, explicitly define the syntax of a language, and then you can formally, explicitly define for all programs what the meaning or behavior of that program is using a formal grammar with these semantic computations. So the difference is it's sort of in your head, implicit, and you hack together a program that you think might be right, versus you have an explicit description of both the syntax and the meaning of this language in a way that you can actually write a computer program that will process for you. Yeah. Yeah, did you have a question? So this is just a little notation to distinguish between the two E's we have here. So this could be like E subscript 1 or something. That's often how it's done. So this is sort of aspects of the meta language that I'm not going to get too far into. But yeah, so this is just saying the first E, the value of the first E in the construct. Questions on this? Does this kind of make sense a little bit? Kind of make sense? So we can explicitly and formally and mechanically define the syntax and meaning of a language in a formulaic, mechanical way. So you don't have to hack together some random Python program to try to interpret strings and try to figure out what they do. You can do this in a formal, mechanical way. Okay, so let's look at compiling this program. So because everyone has done infix to postfix, let me show you how you can use this same scheme to define the infix to postfix problem basically as a compilation problem. So infix to postfix is basically a kind of compiler. My machine froze. Let me see, maybe it's... Oh no.
It's like Ronic.
Okay, so you can think of the infix to postfix program as a kind of compiler, and we can actually frame it as a compiler using our same formal grammar annotated with these semantic computations. You can use the same technique to frame it. But let's go over first what this compiler looks like. So let's take let's take this same program, and instead, I guess I'll do it in blue. Let's do translation rules for infix to postfix. So I think infix to postfix, we don't actually need to know that we don't need to do the mathematical operations. We're just generating strings. So for 8, let's just say blue here is just the ASCII string version of this. And we'll have the same pass-through rules for E. Okay, so what kind of rule can we apply if we have an E, if we have a grammar construct like this that says E op E, that's our infix rule? What computation can we do, or how can we generate code from the information we have on this node that will convert this expression to postfix? Yeah?
Depending on the operator, we can do change it to like we get the individual children, right? Any operator, and then do the operator.
Good, yeah. So we can define as a rule from whenever we see E op E, we take whatever the left ASCII code is, whatever the right string is, and we just say, take the left string, take the right string, and then print whatever the operator is. And so let's do that same process for the parent. So in the parent, we have a left side child that already has the value, which is the string 8, 3 plus, and the right child is 2. And so let's apply the same rule. What do we get when we apply the same rule? Yeah, 8, 3 plus 2, and then whatever the operator here is, plus. Voila. We've just defined the rules for an infix to postfix converter as a compiler that operates over a syntax tree according to our grammar. Questions on that? Does that make sense? Okay. So here's how you might define these rules using our semantic actions that we annotate our grammar with. So here's the same grammar, and we have the same semantic actions for numbers. We just annotate the tree with the ASCII value. Here, instead of converting from ASCII to int, we just pass through that ASCII value. And then in order to compute the output, the value of our expression, we just do string concatenation. We concat whatever the string value of the first expression is, whatever the string value of the second expression is, and the operator. Exactly what your fellow student said. So what's clear, this description of infix to postfix or that stack-based algorithm? Who likes the stack-based algorithm? Who likes the formal grammar? It's about 50-50, or really 10-10, 80 with not answering. But I just want to make clear to you that this kind of formal grammar description plus these semantic rules that you have a little computation that defines the meaning or how you compute the value of a tree that has this pattern. You can define interpreters, you can define translators, and when you did that infix to postfix program, you were really doing a compiler. You were really translating one programming language to another. And we're going to use this same concept in order to create our compiler. We're going to define a formal grammar for the language, and then we're going to define little rules on each grammar construct that says how we generate assembly code for that construct. Questions on that notion? And it's going to work exactly the same way as this, just in Python and with our ANTLR parser generator. But it's going to be the same idea. You'll have a function that gets called every time the parser matches a grammar construct in the language, and you'll define a function that will just spit out assembly code that has access to the values of the components of the construct. Yeah?
So in that case, right, how does our compiler know what an operation does? Or is that already like
Well, so how does this compiler know what an operation does?
Yeah.
Or how does this machine know what the meaning is? Does it know the meaning?
Yeah.
So it depends on your sort of philosophy of mind, but in some sense, this machine doesn't have to know. It's just following rules. And it's the rules themselves that define the meaning of the language. So you as the compiler writer are crafting this machine to kind of behave as if it knows, depending on your philosophy of mind, behave as if it knows the meaning. But really it's just following a set of rules.
So where are those rules like given? How does it know how adding works? Or like how
It doesn't know how adding works. So this doesn't know how adding works. This is just defining a computation to run whenever you see the symbol for add. So remember, this symbol is matching ASCII addition symbol, the ASCII plus symbol. There's no meaning intrinsic in that symbol in the machine because it's just an ASCII code. Its meaning is completely determined by the machines and by us that interpret the meaning of that symbol. And so the compiler is the same way. And it's us as the compiler writers that write code that, depending on what you think of how the mind works, that code is either doesn't know anything about the meaning of it and it's just following rules to make it look like it has the meaning. Or you might think of it as the compiler is imbued with the meaning. The definition of the compiler is the meaning of plus. Does that kind of make sense? Is this too meta? A little bit makes sense? So it really goes back to the distinction between symbols and meaning. So if you can wrap your head around this map territory problem, that the map is not the territory. You know, the symbols that we use to represent something are not the thing itself. So the map is not, you're not going to see people who are walking on the earth on the map. You're not going to be able to rip the map and destroy the world. So the plus symbol is just a symbol devoid of meaning on its own.
So how does it know that what assembly code is like matching?
That's the job of you, to write code that will make the program behave as if it knows the meaning of.
Compiling like C code, do I have to create another compiler in C?
Yes. Yeah. Yeah, if you want to compile P code, you have to write a compiler that processes C code. Because remember we talked about the bootstrapping problem. If you have no compiler for C and you write a C program, there is no machine that will be able to compile that for you. If you write C compiler in C and you have no C compiler, there is nothing mechanical that will turn that into assembly for you until you write that program. So yeah, this is the very mind-bending kind of self-referential trickiness of compiler writing. And it really comes down to this distinction between symbols and what they represent. Now, yeah, there's a lot of sort of philosophical implications to how, this is kind of like the theory of knowledge. Like, is it only symbols in the world? Or do they point to things in the real world? There are various philosophical views on this. But in the machine world, we can at least make a computer look like it can interpret the meaning of symbols using these computational techniques. Yeah.
So does the compiler define symbols?
Effectively, yeah. Effectively, the compiler defines the symbols. Now, some programming language theorists will think that, well, the programming language is defined on its own, and then the machine is an instance of that. But kind of concretely speaking, if you don't have a program that interprets the meaning of this, then at least the machine does not have, has no meaning to the machine. That's for sure, because if you just like give ASCII code to the CPU, for instance, the CPU is not going to interpret that as a plus symbol. So the compiler gives meaning to these symbols by translating them to another language or interpreting their resulting value. And so in some sense, yes, you can think of that, a compiler or interpreter, as an expression of the meaning of the language. Because without it, well, there's nothing interpreting the meaning of that. And so in another sense, you can think of our minds as ascribing meaning to symbols by interpreting what they mean. And so that's what I was trying to illustrate with this, using a different language that I think most people here, no one here actually knows, but there are some humans that will interpret this in the same way as this, that I think everyone here can interpret. And so you could sort of say there's some teleology here, that these symbols are somehow intrinsically meaningful by saying, well, okay, well, there's one stroke here and two strokes here. But that's a little harder to do for the other symbols. You could say that, but the more kind of engineering view, I guess, is that symbols are independent of their meaning. It's a different kind of epistemology, I guess. that symbols are divorced from their meaning. And we can use that philosophy to create programs that will kind of magically or artificially intelligently, in the classic sense, interpret the meaning of symbols in a way that humans sort of do. All right, questions on this? So wrapping your head around that kind of self-referential meta notion and the difference between symbols and their meaning will help you, I think, write the compiler. Yeah?
So the goal of making a compiler is to, you go with parsing and make it into assembler and assuming you make a compiler, well, wouldn't that mean that every language is compiled should have like similar runtimes for lots of stuff? But is it just convention that changes that, or
Yeah, I think it's convention. You mean why do some languages seem to have similar? Well, if they're compiling to assembly, then it's always machine code, and so you're always at the performance sort of. You're always subject to the performance of that machine, and so it's up to you, the compiler writer, to try to have different have assembly output that will have better or worse performance for the same program. I don't know if that answers your question, but.
So it's like an optimization thing?
It's an optimization question, yeah. Okay. To say, how does a compiled program, why would the same compiled program, or a program that computes the same thing in two different languages, why would their assembled program have different performance, right? That's the question.
Yeah, are they always, is there autonomous parts that it's broken down into for every compiler for x86?
Well, yeah, I mean, the instruction set itself are the atoms that compiler writers have available to them. So you can't do better than that. I mean, there's microcode to modify the instruction set, but if you have an instruction set and an instantiation to that in the machine, the compiler writer doesn't really have much else to do besides that. I mean, there may be cache behavior or other aggregate behaviors of the machine that the compiler writer can take advantage of, like caching is a big one, to make sure that you're not kicking stuff out of cache with your order of operations. There's other memory behavior you can do. You can take advantage of the pipeline. But at the end of the day, you're sort of subject to the performance limitations of that machine as the compiler writer.
Okay.
Yeah?
Why in this case you don't have to declare the operator?
Which ones? Oh, declare in this one?
Yeah.
So here I'm not interpreting. I'm not running addition. I'm just outputting. So yeah, this is one other distinction between interpreters and compilers. The interpreter, the resulting value, is a number. That could be an abstract mathematical number. That could be a machine number. In the compiler world, the output is really just a string. So what we're going to output is literally assembly code. An assembly file is just a string. It's just a more ASCII text. So we're not doing any evaluation. We're not trying to find the value that this program computes. We're just translating it to a different program that also ideally computes the same values that the input program does. So remember, you have three programs. There's the input program, the output program, and the compiler program. The compiler is not trying to figure out the answer or the output of the input program. All it's doing is translating it to a different program, a program in a different language that is supposed to do the same thing. Does that kind of make sense? Does that answer your question?
But then you have to change the sign for the word, instead of I think the plus sign you have to add to make it assembly.
Oh yeah, so this is not assembly. This is infix to postfix. So assuming you have an interpreter for the postfix language, but this is not generating assembly. This is generating postfix notation. Yeah.
So after we use an interpreter to perform the addition and then output.
Yeah, and that's what a compiler expects, right? So what's the interpreter for the assembly code? The processor, right? The machine instructor, or I guess it's really the assembler which produces machine code, and then the machine code is interpreted by the processor. But yeah, conceivably, if you have a compiler, your goal is to translate it to a different language that already has an interpreter or a compiler for it already. So for instance, the first C++ compiler, from what I understand, didn't generate machine code, it generated C code. And then there was already existent C code compilers, and so those were used to generate machine code. But yeah, I don't know if does that answer your question? Okay, let's take a look at our intermediate language that we're going to use for our compiler. So we're not going to have to compiler a full C-like language. We're going to start from the intermediate language. It's going to be a simple, a much more straightforward language to translate to assembly than something like C. So here's a C program. Assume I've got a function that can read an integer in, and assume a function that I can print an integer with. So here's an example C program that just reads in an integer, prints it out, then returns 0. Questions on that? Yeah.
Do you use like scanf and print instead?
Yeah, that will be used. That'll be used behind this. Yeah, you could. But let's assume we have this program. All right, questions on this program? Straightforward C. Here is what an equivalent program looks like in our IR language. So you're not going to have to write the translation from C to this. I just want to show you a C version, so hopefully you understand the meaning of this language. But this is what our IR language, our intermediate representation language, is going to look like. The first line of every IR declares the name of the function. It declares which local variables you have. So this is a little different from C. It declare all the local variables and all the parameters. You declare which of those local variables are parameters. And at the very end, you always return. So this function and return are the mandatory parts of IR. And then in the so-called body of our function, it's not really body, it's just a sequence of lines. Here is the sequence of IR instructions that will do the same thing that C program did. So here is what a function call looks like. You always capture the return value of a function call. It's X, and then we have this kind of special assignment symbol to distinguish it from C, I guess. Use the call keyword and the name of the function. Oh, I actually forgot the ×2 in this program. But if you want to do some operation, you can do a single operation at a time, just like in assembly. There's no nested expressions in this language. So this is an example of computing the value of a variable times 2 and saving its result in X. And here's another example of calling a function. So questions on this? Does this anything that doesn't look clear about? I know I haven't gone through the whole language, but anything that doesn't look clear, yeah.
We're gonna be compiling this to assembly.
Yes, you're going to be compiling this language to assembly.
So we can write assembly code, or you can write this as a program.
You can write this as a program, and your compiler will turn it into assembly and run it. I'll also give you an interpreter for this language, so you can check the output against your compiled version. I should be able to show that to you a little today. All right, so it's a much more simplified version of C, but it's compatible with C. The compiled version will be compatible with C. So each file is one compilation unit. One compilation unit defines one function. So one function, one file. This is the minimum program in simple C that you can have. Function with the name of the function and a return, where return takes an integer or a variable name. In this case, there's no variable, so it has to be an integer. So that's the minimum program. Most programs that have parameters will look like this. So you have the name of the function, local variables. Parameters are always a subset of local variables. I promise you this will make assembly generation easier to declare the local variables and the parameters separately. And then you have all your instructions here. So let me go over quickly what the kind of instructions you have available to you. So you have assignment. An assignment is always a variable on the left-hand side, followed by the assignment symbol, followed by either an integer literal, an ASCII symbol for an integer literal, or a variable name. And variable names don't have to be a single character. They're unbounded. Yeah.
What about pointers?
Oh, we'll get to pointers. You'll have to do pointers too. Thank you for asking. They was already going to do pointers. It's not because he asked. We're doing pointers. So that's assignment. So assignment is just copying the value from one either integer literal to a memory location, basically. Does anyone know what assembly instructions might correspond to assignment? Yeah. Move registers, and maybe what about from a constant? Move immediate, if you remember this. Okay, so there's also arithmetic operations. So there's only a single operation per statement here. There's no nested or large expressions. And And you have one operator here, which is just plus, minus, plus, minus, asterisk, and slash. And the operands are either a number or a variable. So no nested expressions. So that's arithmetic expressions. Function calls look like this. Function calls are also assignment statements. You put the name of the variable that you want to store. So even if there's no return value, you have to assign something to it. And in C, actually, void functions are kind of a new thing, but classic C always had a return value defaulting to int. So same in this language. All function calls will try to capture a return value. You have to assign that to something, even if you never use it. And so you use the keyword call. So call is a keyword. The name of the function, which corresponds to some other IR file, or it actually can correspond to a C file. We can actually interoperate between C and our IR here. And then a list of variable names or numbers. So it can be more than one, can be any zero, it can be zero or more than one or more than one. Questions so far on the syntax of this language? Yeah.
So for that line specifically, what if you call X again? Or like you use X for some other purpose, or like you try to print X.
Call X?
Or like print, if you try to print X again.
Yeah, that's fine.
Would it change the value because you're reassigning?
Yeah, absolutely. Yeah, this will change the value. Yeah, just like in C.
Okay.
Like in C, if I say X equals X, yeah, I'm going to redefine X. Same in C.
So print doesn't really have any like output, like any.
Oh, print has no meaning in this language. Print is a function. It's the name of a function that has to be defined. Print int has no. Yeah, these are just names of functions that are soon to be defined, just like in C. So if you call the function, Paul's class parentheses X, you have to define that function somewhere. It's the same thing. Yeah.
Are the arguments separated by spaces?
Spaces, yeah, they're space separated. Yeah, sorry, I didn't make that clear. They're space separated. Okay, so this is where it looks more like assembly. We don't have structured code. We've got branching. So there are unconditional branches that I put unconditional. I didn't put it here. So there are unconditional branches and conditional branches. This is what a conditional branch looks like. Actually, I thought it was just if, not if go to. I'll figure it out. I think it's supposed to be just if. If the if keyword followed by I have to check the syntax to make sure I'm getting this right. So a if go to is just the if keyword, and then so you have a single operand here, which is either a number or a variable, a single operator, which is one of these relational operators, another number or variable, the keyword go to, and then a label name. And so you can also do unconditional branches, which are just go to the label name, and you can make labels with just label name : So just like assembly. Does this any questions on this at all? Hopefully this is familiar from doing assembly code. Yeah. Just if. It's just if. It's just if. Yeah. So the parsing will be handled for you. You won't have to actually parse this correctly, but you will have to write this code. So sorry about the mix up on that. All right. So here's what pointers look like. There are three types of statements for pointers. They're all various forms of memory copy or move operations. So they reflect the similar C syntax. So in C, what does this do? Gets the address. So this takes the address of a variable and stores it in some other variable.
You don't need a star next to it?
For this?
No.
Not in C.
Not because it's T1.
No, not in C. Nope.
You need something to point to the address, no?
Well, T1 should be declared as a pointer.
Yeah, that's what I'm saying.
But when you assign it, you don't use the star. That's in the declaration. So this language is also untyped. And in C, you could actually assign a reference to an integer if you wanted. Compiler might, if it has strict checking on it, might yell at you. But you can do it. You can go take the address and store it as an integer and print it out as an integer if you like in C. You can kind of subvert the type system.
You'll
Yeah.
just change the value of the address, right?
If you modify it, yeah. Yeah, you can do pointer arithmetic in C. Yeah, you can mess with you can mess with addresses in C. But yeah, so this is what the structure looks like. You just have the name of variable on the left-hand side to store it in. There's no types here. There's no type checking, just like in many IRs. Okay, so what does star T1 do in C? Dereference, right, good. So this is the dereference. It'll take whatever the value of the memory, it'll follow the memory location in T1 and then get the value of that of that number in the address. All right, and what about if I assign to star?
That's zero.
What? Say again?
No.
It's taking the reference value of T1 and assigning it to 11.
Right, it's dereferencing T1. So if T1 is an address, so at the end of this, what's the value of X at the end of this? 11, good, yeah. So we're taking the address of X, storing it in T1, and then we're dereferencing T1 to store the value 11. So, T1 is pointing to X's value. Okay, so those are all of the operations in the language. Let me give one example of which has the correct if statement here. Let me give an example of a program of computing an exponent. So remember, all programs start with a function. If you have local variables and parameters, define all the local variables that you're going to use ahead of time, including the parameters, and then define which subset of those local variables are parameters. So this is kind of the header of your program, and then at the end there should always be a return. All right, here's the body of our program. We've got, and it looks very much like an assembly version of this, so we start with assigning result to 1. We've got a label here, because we're going to jump back to it. And so whenever exponent is less than or equal to 0, we stop. We go to the end. So if you input a program that has an exponent of 0, what's the value of any number to 0? It's 1, right? So this will correctly compute that. If it's not 0, then we multiply result by base. So it's just repeated multiplication, right, for exponent. And then we subtract 1 from the exponent. And we unconditionally branch to top and check again over and over and over. Questions on the algorithm for exponent? Hopefully you've seen something like this. Questions on the syntax of simple IR? Yeah?
Are there supposed to be colons before the equal signs?
Yes, there are. Thank you. Yes, there are supposed to be colons before the equal sign. I have a real version of this that I actually ran. This is what it's supposed to look like. Sorry about that. This is what it's supposed to look like. Yes, there are colons before the equal sign. Okay, so I'm not a good mechanical parser. I don't expect you to be either. But your homework for tonight is to take a stab at writing a program in simple IR that computes factorial. You can do it iteratively. You can do it recursively. Yeah. You can just make, you can make a main function. You can make a factorial function. You don't have to call it. You can just make one function. So try your hand at writing a factorial function in this language. And then next time we'll actually start looking at how to compile this language. All right, thanks everyone.